the talk tensor network study of magnetic excitations of triangular antiferromagnetic from Chinese Academy of Science. Runze Chi. Please start slowly first. Okay.
Okay. Thank you, Professor Tomotoshi. And this is my turn. Oh, hello, everyone. I will first introduce myself. I'm Runze Chi, a PhD student in Professor Tao Xiang's group from the Institute of Physics, Chinese Academy of Science. Thanks for the organizer for giving me this opportunity to share our recent work on the triangular antiferromagnets. This work is in collaboration with Professor Tao Xiang, Professor Haijun Liao, Mr. Yang Liu, and Professor Yuan Wan. Recently, the low-dimensional frustrated material has attracted a lot of attention in the community of condensed matter theories. As the simplest realization of frustrated materials, the triangular antiferromagnetics is an example. As as shown by the left figure A, this is a triangular lattice and with the classical E-sin spins. If the site 1 and site 2 spins are coupled antiferromagnetically, they will point to the opposite directions. So that for third spins, the energy will degenerate whether it's a point up or point down. So that this is a realization of frustration. It will increase the ground state degeneracy. For classical vector spins, the degeneracy will much larger because every configuration of the spin 1 will introduce the two degenerate ground states. And the spin on the site 1 will have a U1 symmetries. Therefore, the geometry frustration will introduce a large ground state degeneracy in a classical level. So that's how about the quantum version of the ground state of the triangular lattice antiferromagnet? For these problems, Monte Carlo will encounter the famous sign problems. So we need some new method of theory to solve these problems. Since a lot of effort, the consensus has been reached recently that the true ground state of a triangular lattice antiferromagnet antiferromagnet is actually a classical order with 122 degrees between them, but the magnetization is largely reduced compared with the classical limit. Although the ground state is much more classical, the theoretical prediction of the magnetization curve shows that there is a famous 1/3 magnetic plateaus, which is contradicted with the classical spin predictions. And the excitation spectrum predicted by the series expansion also indicates that there is a large discrepancy between the linear spin wave prediction and the series expansion. Therefore, the excitation in the triangular lattice antiferromagnets is very different from the classical spin. However, the correctness of the theoretical prediction need the further experimental verifications. Thanks for the progress in the experiment. The material barium, cobalt, antimony, oxygen has supplied such a playground for us to study the properties of a triangular antiferromagnet. The lattice structure of this material is shown on the left-hand side, and the cobalt iron from a triangular, two-dimensional triangular lattice with the antiferromagnetic Heisenberg interactions. There is a little implies anisotropic for this effective Hamiltonians. The parameters is estimated through a lot of experimental techniques, as the exchange coupling of the antiferromagnetic coupling is 1.67 milli electron voltage, and the little imply anisotropic is 0.95. The neutron scattering measurement on this material can help us clearly see the magnetic excitation in the triangular lattice antiferromagnet. The right-hand side shows the Brillouin zone of the triangular lattice, and the momentum path along the h directions is the experimental measurement is along this momentum path. First through the gun point, and then the K point, and the M point, and back K point, and then gun point. From the left-hand side, we can see that the white line is the linear spin wave theory predictions. First, let's look at the low energy regions. The color side is the neutron scattering result. In the low energy regions, the linear spin wave theory prediction fits the experiment very well. So with gapless Gladstone mode due to the symmetry breaking of in-plane rotation, and two gapped Gladstone mode due to the little anisotropic in-plane anisotropy. However, for little high energies, we can see that around the endpoint, which correspond to the Q equal to 0.5 Q in the endpoint, the linear spin wave theory predicts that there will be 3 branches of magnons. However, the experiment found that there are only 2 branches of magnon which are large renormalized downward energy dispersion, and there is a 2 Rotan minimum around the endpoint. The right-hand side uses a much more high energy incident neutron energy, so that we can have a broader view of the spectrum of the high energy regions. It can be seen that the spectrum can extend up to 6 million electron voltage, 60 electron voltage, which is much higher than the 2 magnon continuum, upside of the 2 magnon continuum. Therefore, the theoretical, the experiment finding is very different with the linear spin wave theories. A similar experiment, but with a higher resolution on the same material, clearly shows that there is a 3-stage characteristics. First, in the lower energy regions, there are 2 soft Rotan-like minimum at the endpoint without decay. And at the higher intermediate energy region, there is a W-shaped dispersive continuous. And in the higher energy regions, there is also a W-shaped dispersive continuum. The right-hand side shows that the spectrum cut along the endpoint on these lines. It can be clear see that there is 4 peaks along the energies. The lowest one is the 2 magnon peaks, and the higher broad ones cannot be expanded with the magnon pictures. With this experimental finding, we are left with the impression that the excitation in the triangular antiferromagnetic is very different from the classical pictures. Can this be explained by a theory? One more step beyond the linear spin wave theory is considered the 1/s corrections. In the triangular lattice antiferromagnet, the ground state order is the non-collinear, so that the first order correction in the 1/s will include the cubic term, which include the 3 magnons interactions. The 3 magnon interactions will easily lead to a magnon decay. If the single magnons and if the magnon energy equal to another magnon, sum of 2 other magnons, the decay regions, the decay will lead the instability of the magnon branch. The decay region is shown on the left-hand side here. It fills a lot of regions of Brillouin zones, and the central figure shows that the prediction of the 1/s corrections along the momentum path as shown on the right arrows. It can be clearly see that the right line is the 1/s corrections, and the blue dotted line is the linear spin wave theory prediction, and the gray areas indicate the decay regions predicted by the 1/s corrections. You clearly see that the 1/s correction successfully explains the large downward magnon branch compared with the linear spin wave. And also, it predicts there is a local Rotan-like minimum at the endpoint. And the linear spin wave theory predicts this will be a saddle point. However, As we have seen that the experiment have two local rotor minimum around the endpoint. Another branch of the magnon actually come from this point. It's because our ground state has the magnetic orders, which magnetic order, so the magnetic brilliance is shrink. So that's the magnon branch this magnon will be folding to this point. So that's is the contribution of the second branch of magnon around the endpoint. As indicated by the one-over-S correction, this point show a larger of magnon decays and it's non-analytic behaviors. It's not consistent with the theory, with the experiment to show that there is a sharp magnon minimum. To further prove the correctness of the one-over-S correction, Professor Gemma's collaborators do a careful comparison between the experiment and the one-over-S corrections. It shows that between the real materials has a little anisotropic, in-plane anisotropic, the decay region will largely shrink. So that for true materials, the one-over-S correction predicts that magnon will be very sharp, and it's different with the experiment. So he concluded that the large S treatment are not enough to explain the experiment to observe the magnon decay. And also the recent high resolutions inelastic neutron scattering experiment show that the magnon branch actually is very sharp. Another perturbative method based on series expansion also shows that there is a large downward compared with the linear spin wave theory prediction. The black dot is the linear series expansion result, and the green curve is a one-over-S correction, and the red curve is the linear spin wave result. Based on this method, the second branch of the magnon shown in these blue circles has a more analytic behavior, but it also do not show a second rotor minimums. The author of these articles suggests that the rotor minimum is maybe from a repulsion effect from high energy and from the high energy of the two spin-on continuums. Because the experimental finding that the magnon branch is actually very sharp without decay, another scenario beyond the perturbative method based on the density matrix renormalization group proposed that another scenario that avoid the quasi particle decays to explain the second rotor minimum around the endpoint. The picture is as the following. Suppose there is a single energy level penetrate into the continuums. If the interaction is very low, it will decay as indicated by the 1/S corrections. But if the interaction is very large, such as in our small spin limit, spin equal to one half spin, the large repulsion, the large interaction will push the energy level out of the continuum and to become the avoid the quasi particle decays. They use this picture to explain the second rotor minimum observed in the experiment as shown by the Y1 point. Because the Y1 point is connected by a primary vector of the magnetic brilliance zone to the endpoint. It's more clear in these pictures. The epsilon1 is the first magnon branch, and the epsilon2 is the second rotor minimum. And they explain the second rotor minimum as that the original magnon branch will penetrate into the continuums, and the two magnon continuum, which is composed of the epsilon1 plus the gapped Gladstone mode here to form the edge like this. And the larger repulsion interaction between the continuum and this single magnon will push the magnon branch here and form such a second rotor minimums. Although this scenario successfully explains the second rotor minimum, it's restricted to its finite later ways. This is the difficulty of the DMRG method, so that it has only finite momentum point. And also the Hamiltonian the author used is actually easy axis Hamiltonians, not experiment easy plan Hamiltonians. This avoid Christ particle decay is also proved by another by Ferri and Baker using a different method based on the variational Monte Carlo simulation based on the path flux RVB state rather than the valence bound state. The white dotted line show clearly the 2 magnons continuum, the lower edge of the 2 magnon continuums, and the lowest one is a single magnon branch. It's clear to see that this 2 magnon continuum is on the upside of the single magnon branch, so that there is no crazy particle decays. Based on this series, the author also predict that there will be 2 downward as around the endpoint. One is from the endpoint, as indicated by the orange lines, and one is from the Y1 point, which is folding to the endpoint through the Brillouin folding. Then there is also downward. The blue line is the series expansion, as I have explained before. It cannot predict the second downward. The similar picture based on the spinons has also adopted by the Professor Tao Li and Chun Zhang. They use the spinon pictures. They use the spinon picture, but based on the phenomenological treatment. They also suppose the RVB state with a U1 flux state, so that the spinon dispersion has 2 direct points around. And to reproduce the magnetic orders in the ground state, they use they add phenomenological parameters to produce this effect. They use with the properly chosen the parameters. They predict that the endpoint around the endpoint there will be 2 magnon branches instead of the 3 magnon branch can be observed by the experiment. And above this magnon branch there will be a broad 2 spinon continuums. And around the K point there will expect the 3 magnon branches, and they also predict another sharp mode. The author concludes the dramatic change in the endpoint can be attributed to the level portion between the 2 spinon continuums and the lower collective spin excitations. The reason why the effect is much sharp on the endpoint is because the vectors connected to spinon direct point is the vector of the endpoint. And they use to further classify the origin of this mode. They calculate the polarization of this spectrum, and they conclude that the black line, blue line, and red line is 3 branches of transversive magnon modes. But the third transversive mode, the spectral weight indicated by the green dotted line, is eaten up by the spinon continuum and cannot be seen by the experiment. And he also found another longitudinal mode around the K point. Although the series has successfully explained some characteristic of the spectrum, especially the low energy parts, so far all existing theory and numericals cannot quantitatively reproduce the full energy spectrum from pure macroscopic models. And compare directly with the experiments. And also, in particular, no theories and numerical method can give a good explanation about the feature of the intermediate regions here and the high energy regions here, these 2 broad peaks. They only predict the low magnon branch. The Tensor-Network method has supply a very good start point because it's some problem free. So it can be easy. We can use it easily to start the frustrated triangular antiferromagnet. The ground state is a triangular lattice antiferromagnet is shown on the left-hand side. There will be 3 equivalent points from in a magnetic unit cell labeled by a blue triangular. Here we adopt the ansatz to group these three sides in a magnetic unit cell together, so that the triangular lattice is transformed into a square lattice. It transformed to a square lattice with the physical index as a physical dimension of 8, so that we can study this problem on only a square lattice infinite path structure without need a much difficult method. To solve the ground state problems, we need to do a rational calculations. It's actually optimization problems to optimize the single tensor A based on the ground state energy. It's actually a nonlinear optimization problems, and this optimization can be done through a gradient search. However, the gradient is difficult to get through a conventional method. Professor Haijun Liao and his collaborator proposed that this can be done through the method from machine learning, through the automatic differentiation. This method can help us easily calculate the gradients of the effective energies, so that we can, without too much effort, so that we can get a high precision ground state. And this ground state will be crucial prerequisite for accurate excitation. The excitation based on the IPAP's ground state this is proposed earlier by the Van der Steen in 2015. It's a Tensor-Network version of a single mode approximation. It can be done by replace a single site of a ground state by impurity tensors and linear compose them together to form the eigenstate of translation operators, so that we can calculate the excitation energy in each momentum sectors. The effective Hamiltonian is composed through the excitation ansatz overlap with the Hamiltonians. The difficulty in this method lies on the overlap between the ansatz and the Hamiltonian need a threefold of sum over all the lattice sites. And it's difficult to do through conventional method. And recently, Paulson has pointed out that the method based on the automatic differentiation, so that the effective Hamiltonian in his method is expressed as a gradient. This help us to easily to calculate the effective Hamiltonians and the effective normalization matrix, and these can be transformed into a generalized eigenstate problems. With this eigenstate ansatz, we can also calculate the spectrum properties, which will help us further clarify the excitation properties. Another point need to be pointed that due to the excitation ansatz actually form a complete basis in the tangent space. I think it form a tangent space. You can prove that you can prove that or numerical prove that it satisfies a famous a kind of sum rule. The sum rules means that if we sum over all the dynamical structures, spin structure factor together, and we can get the same value as directly calculate the static structure, spin structure factor, as shown by the left-hand side, the red line and the blue line is overlapped. This means that if the bound dimension is our ansatz is large enough, it will have a better resolution of all the energy regions of the single particle excitation. This method is actually unperturbative and is really infinite 2D system, so that the momentum can be chosen continuous, and there is no parameters and some problem free. And this is the result of our method to be used for this effective Hamiltonian, as shown by the right-hand side. We use the same parameters determined by the experiment as the 1.67 milli electron voltage exchange coupling and 0.95 milli implying isotropic with a D equals 4 ansatz. The right-hand side is the experimental experiment, and the left-hand side is our result. It's amazing that our simulation result can reproduce nearly all the characteristics of the experiment finding, such as around the endpoint, or the moment pulse is shown as the blue arrows on the left-hand side. For the low energy regions, around the endpoint, we clearly produce 2 rotor minimums and with the same energy as the experiment, can be directly compared with the experiment. And in the intermediate energy regions, we produce the W-shaped dispersive continuous, and in the much higher energies, we can also produce a large W-shaped continuous. And there is a very sharp peaks can be directly compared with the experiment. Besides, we also calculate the spectrum intensity along the endpoint. It clearly see that the experiment finding the 4 peaks could also be reproduced by our simulations with 2 sharp magnum peaks and 2 little broader peaks. And finally, for the high energy regions, the experiment finds the magnum find the spectrum can reach up to 6 millielectrovoltage, and our simulation can also show this point. This right side is our work of the simulation. To further clarify the physical origin of this spectrum, we also calculate the polarization of the spectrum. The y directions is chosen along the magnetization orientation on the A sublattice. So that the ZZ directions will be out of plane transverse directions, and XX and YY directions will be in-plane directions. The right-hand side is the total spectrum plus the energy level. And it can be seen that the lower is the magnum branch is actually still the 3 magnum branches, which is consistent with the linear spin wave predictions. However, the 3rd branch of magnum cannot be viewed by the experiment because it has no spectrum weight. So that the experiment finding is only 2 magnum branches here. And this and the lowest rotor minimums actually come from the out-of-plane transversive mode, and the 2nd magnum branch with a little rotor soft is actually from the in-plane transversive mode. In the intermediate regions, we can see that the out-of-plane mode contributes a little. It mainly contributes from the in-plane mode. And in the high energy regions, the much higher energy regions, it can actually come from the hybridization between the in-plane mode and the out-of-plane mode. This conclusion of the polarization of spectrum can also be verified through the polarized neutron scattering result. However, because the triangular lattice is actually with a non-collinear magnetic orders, if you only measure as the x-axis directions and the y-y directions, the in-plane transversive mode and the in-plane longitudinal mode will hybridize, so you cannot classify them. So that to further clarify this problem, we calculated the sublattice polarization spectrum and on the A sublattice. The local spectrum is equivalent to on the A sublattice, C sublattice, and the B sublattice due to the rotation symmetry. The momentum path is chosen along the primary vector of the magnetic Brillouin zones. And it can be clearly see that the lowest 3 magnum branch have different origin. For the first branches of magnons and the 3rd branch of magnons is mainly come from the out-of-plane transverse mode. And for the 2nd branches of magnons, it comes from the in-plane transverse mode. And they both are pure transverse mode without the longitudinal component. And we also found that there is a V-shaped regions with no spectrum weight left, maybe because due to the interaction with the high energy regions and its spectral weight is eaten up by the high-energy part. For the intermediate regions, we find that for the longitudinal mode, there actually are two longitudinal modes, one here and one around the K point, one is here and one is here, which is beyond the Professor Tolly's predictions, and we find another longitudinal mode here in the intermediate energy regions. Another interesting point of our finding is that we find that for the intermediate energy regions, there is a large spectrum left by the implant transverse mode. This maybe explains the third broad peaks observed along the endpoint, the spectrum. The white line is a spin result. It can be seen that the spin wave results already penetrate into the magnon continuums, and maybe the single magnons interact with the continuums and be pushed out to the downside, but its spectrum weight is left on the high energy regions and contribute to the third broad peaks observed in the experiment. And for the higher energy regions, this point, which contributes the fourth mode observed in the experiment along the endpoint, it actually comes from the hybridization between the longitudinal mode and the transversive mode, both from the in-plane and the out-of-plane mode. Okay, in summary, the tensor network method can perfectly reproduce the inelastic neutron scattering results from a triangular lattice XSZ model with a little in-plane anisotropy without any free parameters. We don't need to make some perturbation or the approximations with the real parameters can be directly compared with the experiment. And compare with the spin wave result, we see that there is a spectrum which transfer from the low energy part to the high energy mode, as I have indicated before, the transversive mode from low energy to the high energies. And this spectrum with the transverse displays a strong coupling between the low energy mode and the high energy modes, which may result in the strong downward of the experimental found the magnon branch, strong downward of the two magnon branch. It's interesting to apply this tensor network method to the more challenging problems in the condensed matters, and I hope that it will help us to clarify more and more two-dimensional excitation problems. And thank you. This is my talk.
Thank you. Now the talk is open for question. Is there any questions? Well, I have one question.
Okay.
Speak about the construction of the excited state, which has a certain momentum K. You have put B tensor some point and taking the linear combination. So it is natural that such a construction is quite efficient for the excitation, such as the spin wave and so on, which is caused by the local excitation and those substitution. But it seems that from the spectrum, you have captured very high excitation, and those excitation might involve several Kesai particles and might be spreading out. So do you have any insight why you can capture those complicated excitation from these simple ansatz?
Oh, I see. I understand your problem. Actually, I first say that linear spin wave theory is different from this ansatz because it's a low energy effective theory. It will not perturb only a single impurity tensor. It will perturb a lot of tensor here. And why our ansatz can reproduce nearly all the experimental finding lines like the bounded dimension. I think that maybe you can say that there is only one impurity tensors, but the bounded dimension here will produce a large of correlations between this impurity tensor and other tensors. And this effect will cause a large local excitations here. And this is non-perturbative method, and this is based on non-perturbative calculation. And I have said that this method have satisfied some rules. It means the excitation ansatz form a complete basis in the tangent space. You know, the single operator acts on the ground state, like the S alpha K as on the ground state, is a component in the tangent space, and our ansatz form a complete basis in the tangent space. So I think it's the crucial point why our ansatz can capture all the characteristics from the low energy to the high energies. And another method based on the perturbative method, it can best capture the low energy regions. For the high energy regions, they may be make some errors. I think so.
Okay, thank you. Thank you for the explanation. I capture roughly capture the mechanism. Okay, is there any other question? Can I ask you the detail or some details of the numerical calculation? So what's the number of maximum chi and how large is the size of the unit cell you have chosen?
Oh, we choose the fixed chi. You can see that we use the bond dimension 4 and the chi is fixed to be the 50. Chi is equal to 50. And the unit cell is 1 because our ansatz is we group the three inequivalent set into a single one with the physical index as 8. So our ansatz has only unit cell 1.
Okay. So such as small unit cell is okay, but it's unit cell.
Yes, it's unit cell because the physical index is not 2 but 8.
Okay, I understand. Okay, is there any question? Okay, Ueda-san, please.
Okay, so thank you for your interesting talk. Okay, so could you show me again the SQ omega in low energy region?
And low energy regions, you mean this one?
Yeah. So in this figure, actually in the experimental data showed very strong peak around the K and the K prime point around zero energy region.
Oh yes, you mean
that in the, but in the IPEX case, very weak intensity or zero intensity appears in the zero energy region around K and K prime point. Why such a discrepancy appears in this?
Oh right, these are good questions. You mean that the experimental finding is more diffusive than our mode. Our mode is more coherent. I think you can understand this from the 2 points. The first, they all be because our ansatz has only finite bond dimension equals 4. With such a small bond dimensions, we cannot capture the interactions of the long range. You know, the bond dimension is small, so the correlation length is small. So that the diffusive behavior is actually come from the interaction between the single mode with the 2 magnons continuous, so it will be diffusive. So that we cannot perfectly capture the 2 magnon continuums. And the second one is because the smaller bond dimensions, we cannot capture all the interaction between the low energy and the high energy, which contributes to the diffusive behavior here.
Okay.
Okay, I have a question. Runze, I'll just follow Lixiu's first question. So for me, it seems like your excitation wave function ansatz is just a block wave function. So that's the key point. It's about the periodicity here.
Yes, it's periodic here due to the sum over on the old side. This what do you mean?
Yeah, just you just put one impurity in the whole network, and you just sum over all the configuration just with the phase shift, some sort of it.
Oh, right. You also want to ask why these ansatz can capture all the characteristics of the experimental finding, right? With such a approximation, I think it's because it's not actually a single mode approximation. It's based on the Tensor-Network version of the single mode approximation. So that's the bound dimension here. It has a larger dimension as the these 4 squares. So there is a large space can be captured. There are large space can be captured by this ansatz. It's not just a single mode approximation, but it's still a local excitation. This is right, but this local excitation, the range of these local excitations can be extended to a much broader regions, which the increase of the bound dimension D. So that for a higher bound dimension D, we can have a local excitation which is much higher the energy the size. Not a single site.
Yeah, yes, I get this point. I just wonder whether there is a relationship with the Bloch wave function because you catch the periodicity here. So it's just the Bloch wave function you see, like the Bloch theorem here.
Right.
It's just the first sight is that way.
Right, because we want to construct our eigenstate of translation operators, so that we can solve the eigenstate in each momentum sectors.
This is already the basis, just like, okay. Okay, again, thank you.
Thanks.
Okay, thank you. Because of the time is up, so let's thank the speaker again.